Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so it's my pleasure to introduce Ross Tate here, who's interviewing today. And so Ross is a student of Soaring Learner at University of California, San Diego, where they do have nice weather. And he's well known here at Microsoft already because he did 2 internships here and he won the Microsoft Fellowship 1 year. He did a lot of work on category theory of effects and compiler optimizations. And he worked with Red Hat on a new language called Ceylon. And today he's going to talk about to us about usability to optimization.
So hello, as Dan said, I'm from UCSD and I research programming languages. And one thing I've been working towards is making programming languages more usable. And how I've been going about doing that is by improving the technology for program optimization. But before I really get into all that, I want to give my overall perspective of programming languages. So the way I see it, people have this amazing ability for intuition and creativity. And they've applied those abilities in order to build computers, which complement them with the ability to process large amounts of data and calculate them with high precision, and which, since their invention, have become ubiquitous in our society. Yet these computers aren't really useful to us if we can't get them to do what we want them to do. And so I view programming languages as a sort of means of communications between these two worlds that enables people to enable computers to enable society. Now, having this role, this means that programming languages suffers from all the problems that people have, all the problems that computers have, and all the problems that communication has. And so there's a lot of ways that we can work towards improving programming languages. One of these problems is that programming languages always have to balance between human usability and computational efficiency. And so this is where my work comes in. I'm working on improving technology for program optimization so that way we can take the emphasis off on computational efficiency and focus more on human usability. And the reason why I think this is important is that in my experience, I've seen that a lot of people sort of always keep efficiency on their mind as they program. And I had a recent example of this pop up at UCSD in our grad student lounge where someone had written this program here. And the details of this program aren't very important. What is important is that another random person came along about a week later and said, oh, by the way, your program sucks. It could run faster by taking this out of the loop. And then another week later, another random person came along and said, well, this is only a case that the optimizer sucks. Typical optimizer will take care of this for you. And then another person says, yes, let's rely on optimization technology. But then another person came along and said, well, how do you know the string is immutable, right? If the string is being changed, then this value of Sterling can change as well. But then another person came along another week later and said, well, actually that doesn't matter, presumably because you can look inside this loop and inside Sterling and see that neither of them modify the string. And so it's effectively immutable through this block of code, and so that value won't change. And so there's this month-long discussion amongst a bunch of random grad students about this.
It's not run in parallel.
Yes. Sorry, I usually say that, I forgot.
Where's the error check? What happens if there's things besides numbers in the string?
Well, yeah. Far more detailed than we were thinking at this point. So the interesting thing is that there's this month-long discussion amongst random grad students about random program, and this whole month, not a single person noticed off by one error here. And so this bugs me because it means that we're focusing on very detailed things like efficiency and whether it's being compiled, optimized, or not compiled when we don't even have a correct program yet. And to prove this actually happened, I took a picture. And you can see I removed some of the inappropriate comments. And the goal of my research is to make it so that you can write the code the way you'd like to, not worry about performance and efficiency, let the compiler take care of that for you, and that way you can focus on the more important things like correctness.
So are you also assuming I is automatically initialized for you?
Yes, I think that should be somewhere up there. And yeah, there's many things wrong with this code. Again, as someone like, I guess probably it's just TAing.
It probably wasn't undergraduate.
Oh yeah.
Well, it wouldn't work anymore.
But all right. So there's already a lot of stuff on program optimization, right? And the issue, though, is that a lot of this technology out there relies on sort of a lot of repeated manual implementation effort that makes it sort of a black box that the typical programmer can't do anything with. It's just something that works by magic, and they can't affect it. And so what I've been doing is going through these technologies and replacing them with these more reusable axiomatic systems that are automated and have a more open interface that programmers can interact with them. And so some areas I've looked into so far are things like translation validation, which makes sure the compiler or the optimizer does what it's supposed to do and doesn't actually change the semantics of the program. And looking into things like extensible compilers, making it so that we can easily add new optimizations to a compiler, and even inferring optimizations entirely automatically, so that optimization will be available for new languages as they're being designed. Now, these three applications here are all sort of unified by this one technology I came up with, which we call equality saturation. And this is sort of an axiomatic way to reason about programs. Now, this is the overall layout of my talk, so feel free to ask questions at any point. Right now, I'm going to start off with translation validation, and I'm going to do so by asking you all a question. So, how many of you have had the compiler actually inject a bug into your code? That is, you went through all this effort to make your code nice and angelic, completely bug-free, only to hand it off to the optimizer, which through some fault turned it into some demonic code that does something that you didn't tell it to do.
I wrote that. Demonic optimizer.
So for those of you who have been so fortunate as to avoid this situation, not cause the situation, let me enlighten you as to how this goes. So if you run into one of these bugs, they're absolutely a nightmare because you can look at your code for hours and say, it should be doing this, it should be doing this, I don't get why it's doing or not doing this. And the fact is, it should be doing that because your code is fine. It's the compiler that's wrong, and you just don't realize it. And furthermore, whenever you try to observe the bug, say by inserting print lines or running the debugger, that shuts off the optimizer, so all of a sudden the bug goes away. So it's like there's quantum physics happening inside your code, which, like quantum physics, can be very confusing for a programmer. Furthermore, once you've finally figured out that the compiler is at fault, then you have to figure out how to rewrite your code in some weird way to make it so that it stops introducing this bug anymore. And all your coworkers get confused as to why your code is so ugly. So as you can see, this is frustrating for a programmer, but it's not only frustrating for programmers, it's also frustrating for companies. And many companies have a policy of not using these optimizers because they can't afford these kinds of bugs. And they do so at rather high cost. After all, this means they have to pay all their programmers to do these optimizations by hand, and hand-optimized code can be more difficult to maintain over time, and so these costs accumulate over time as well. And so these companies would really like to be able to use one of these optimizers, even though it's a little glitchy, because typically they do work, right? So how can we go about doing that? Well, we can consider a single run of the optimizer. We have this original program and optimized program. And we can incorporate a technology called translation validation. And what this does is it looks at these two pieces of code here and tries to figure out whether or not they're equivalent. If it succeeds, that means you can use the optimized code safely because you know it's the same as the original code. You haven't introduced any bugs. And if it can't figure this out, well, then you just default back to the original code just to be safe. Now, there's many ways to build translation validators. The most common one is to use by simulation relations to sort of try to figure out how these two programs walk together step by step. But these things have some difficulties with bigger rearrangements of code. And so we've looked into another way to do translation validation using equality saturation. And so to illustrate my technique, I'm going to start off with a very basic kind of program, basically just simple expressions here. And we'll elaborate to more complex programs as we go. And we consider, OK, this I times 2 plus j times 2, we'll hand it off to the optimizer, and it turns into I plus j, let's shift by 1. And we wanted to figure out whether or not these two programs are equivalent. Now, the idea I had was, let's take these programs and turn them into nice mathematical expressions. And once we're in this nice mathematical world, we can start applying nice mathematical axioms to reason about them. So we know, for example, that anything, or less shifting by 1 is the same thing as multiplying by 2. So that tells us that the optimized program is equivalent to this intermediate program here. Similarly, we know that multiplication distributes to addition, and so it tells us the intermediate program is equivalent to the original program. And so just by using this very basic language axioms, we can figure out that these two programs are actually equivalent to each other. Now, this works very well for these nice, clean mathematical expression programs, but we wanted to make this approach work for more realistic programming languages like C and Java. And so we had to figure out how to accommodate challenges like loops, which I'll go into later on, and effects. And the issue is that typical imperative languages have things like statements, which can not only do mathematical expressions, but also can read from the heap and modify the heap. So we wanted to figure out how to represent these statements as mathematical expressions. And so to do this, what I came up with is to adopt this concept of effect witness. And what it does, it takes this dereference of R here, and it represents this as the expression load from location R from the current state of the heap sigma. And so all uses of the heap are explicit in our representation. Similarly, when we modify the contents of R here, well, then we map this to a store, which not only takes the value to store and the location to store to, but also takes the state of the heap it's modifying, and then returns the new state of the heap after the modification is done. And so all modifications of the heap are also explicit in our representation. Now, if we consider this program here in some more detail, what we're doing is we're taking the contents of some location and then putting those contents back into the same location. And so assuming a reasonable memory model, this program really doesn't do anything whatsoever. And so we'd like to be able to reason about that with our mathematical expressions. And the way we do so is we say whenever we have an expression that looks like this one, well, then the store is actually going to be equivalent to the original incoming heap sigma. And so with these kinds of occasional reasoning, not only can we reason about the values of programs, but we can even reason about the effects of programs. So with this approach, I designed a translation validator that works for C, and we've implemented so far for C and Java. And it takes these two programs, the original optimized program, and these programs come in the form of a control flow graph, right? The standard representation of imperative programs. But this isn't very good for algebraic reasoning, as we found out. And so what we did is we came up with a new representation, one that I call a program expression graph, and we converged to that. And the reason why we call it a program expression graph is that it represents the entire program, or really the entire method, as a single expression that forms a graph rather than a tree because it has some recursive loops in it. And so once we have this nice mathematical representation, well, then we can move on to equality saturation. And what this does is it applies those algebraic axioms in order to infer equivalences, and hopefully you can figure out that these two programs are equivalent. Now, to get a more detailed picture of this, let's consider this program here. And don't worry about the details of this program because it's just contrived to illustrate how my technology works. But let's suppose we hand this off to an optimizer and it spit out this optimized program here. Well, we can all look at this and say, well, what it did is it took these two dereferences of P here and stored that into a temporary local variable that it used twice. Similarly, we had these two multiplications by B here, and we simplified that to a single multiplication by B. And so what the translation validator has to do is figure out how to figure that out entirely automatically. And the way ours goes about doing that is first taking this original version of F and converting it to a program expression graph, our own representation. And so to do that, we take this dereference of P here and translate that to a load that takes the location P and the incoming state of the heap sigma. And then this call to stir here gets translated to this call with these two parameters S and the result of that load, operating on the current state of the heap sigma, and has these two outputs. And what these two outputs correspond to is this pi v node is the returned value of the function call. That is the value being explicitly into this x here. Whereas pi sigma is the resulting state of the heap after the function call completes. In particular, when we have this next dereference of P here, well, then we use that new state of the heap rather than the original state of the heap. And so we distinguish these two loads in our representation. Now, then we go on to this additional multiplications here, which we store into the heap in order to get a new state of the heap for the function. And lastly, when we return x, we mark that this pi v is the returned value of the function, whereas that store is the resulting state of the heap after the function call completes. Once we're done with the original program, well, then we move on to the optimized program and do the same process, which I'll skip over. But we're going to reuse nodes as much as possible in order to simplify and speed up the process. And at this point, once we have this nice mathematical representation, we made sure it's complete so that we can actually throw away the original control flow graphs and just work on this mathematical system. And so we can start applying axioms. So one is the fact that multiplying by 2 is the same thing as subtracting by 1. And so knowing that, we can add this equivalence here. And note that we're adding an equivalence. We're not throwing away the original program. And this is how we differ from a lot of other techniques, which are more destructive. And this is how we make our system able to adapt to a variety of compilers and a variety of optimizations. In particular, in this situation, this left shift by 1 isn't actually useful for this to validate this translation. Rather, we want to use this additional multiplications and apply distributivity. Once we're done with the math up there, we can move down to the function call. And we can incorporate some knowledge that we know that LLVM, this optimization framework that we targeted, is using. In particular, LLVM knows that this call to stir doesn't modify the heap. And so the state of the heap after the function call is going to be the same as the state of the heap before the function call. And so we can add this equivalence to representation. And once we've done that, well, we have these two loads from the same location, and now we know that we're operating on the same state of the heap. And so we know the result of the loads is also going to be the same. And consequently, the result of these additions is going to be the same, and the result of these multiplications are going to be the same. And then transitivity tells us this addition is equivalent to that multiplication. So this leaves us with these two stores. And we can see they're operating on the same state of the heap at the same location, and now we know they're storing the same value. And so they're going to result in the same state of the heap after storing as well. And so what we've just proven is that the original f and optimized f have the same overall effect. And so all we have left to prove is that they have return the same explicit value. And this is really easy in this case because they actually started off with identical values in our representation. And the reason why that happened is that our representation, being mathematical, gets rid of all the intermediate variables. And so a lot of syntactic differences between control flow graphs sort of go away. And in fact, many optimizations are validated just by translating to our representation without even having to apply these kinds of equivalences.
Where does alias analysis come into the picture?
So alias analysis we'll use to know if we have a load and store that the resulting effect indices sort of can commute with each other. So if we have two stores, then they can commute past each other. If we have one load, we know that if we have a load and a store, and they're the same location, then we just use the same one. But if we can prove they're different locations, then we just reason that the load is going to be the same as before the store as after the store.
But if there's been severe code motion, how does that work with alias analysis?
Oh, so I mean, you're talking about how do you make like the alias analysis itself?
Well, right. I mean, there's the aliasing on each program, but there's also sort of the equivalences across the
I see.
When you're moving code.
So, like the fact that there's two programs actually doesn't really create too big of a problem for alias analyzing, because there are still values within the programs, and so it's usually within the programs that you know the operators commute. And then once you figure that out, then you'll figure out okay, these two values are the same across the programs. So the alias analysis tends to be within two programs or within the program itself. And so it's not a big problem that there's two programs going on.
Alias program point-specific alias information that you use to sort of refine your conversion into the peg.
So we use so what I'm showing here is actually very simplified. Like we have things like ordering analysis and stuff like that, so knowing whether one integer is bigger than another and stuff. And we have alias analysis as well, and these can all work on top of this kind of basic system. Yeah. Usually, so alias analysis, because we're doing this entirely automatically, we often don't have alias information. So actually, this is a problem that we had with LLVM was that even though we told it not to, it would do an interprocedural analysis to figure out alias information and then do optimizations that weren't valid from what we could know.
Right.
But if we had it set up so that if you gave it to us, if you actually gave us the information, then we could start applying it.
I see. So you have a way to incorporate alias analysis.
Yes.
That's a question. So you're trying to prove equivalence under an arbitrary context, right? What if there are preconditions that enable the optimization?
Right. So this is basically the same thing as the alias, right? There's some preconditions, some fact about your inputs that we don't know about, and so if you give us the information, then we have the logic for reasoning about it, like we do for alias analysis and a few other things. Then we can prove stuff about it, but we can't infer the context. We're an entirely intra-procedural system.
So basically what you're saying is, give me any kind of proofs of your program, and if I can use that to add more equivalence arrows.
They don't even have to be equivalences. There's actually systems, you can put arbitrary logics on top of this. Well, not arbitrary, but many logics on top of it.
You can only use that if you can improve your graph somehow, right? Like here with Sturgar, you improved it because you added this yellow equivalence that you said, oh, it doesn't modify the heap.
Right.
With an alias, you would do the same. So what other things would you do besides adding?
With the alias analysis, what you do is you actually tell us these things are distinct, and then we'll infer the equivalences from that. So we'll infer the equivalences. You don't have to give us the equivalences.
Oh, okay.
But same with inequalities and stuff like that. Sometimes we'll take advantage of inequalities and use those to infer things, or particularly bounds and integers to deal with overflows and stuff like that. Okay, so going back, we've proved that the return values are identical and the overall effect is identical. So we basically just validated this optimization, right? And we were able to validate a wide variety of optimizations. So to test this out, we ran this on the LLVM through the Spec 2006C benchmark suite. And what this last column indicates is that if LLVM made some sort of change to the program, then 3 out of 4 times we were able to validate that change. And what's cool is that another team of researchers actually came along and implemented their own translation validator, specialized towards LLVM, even specialized towards this exact configuration of LLVM. And while this did get them significant performance improvement, they actually were only able to match our validation rate. That is, they actually weren't able to improve their success rate by the specialization process. And so this is important. Sorry, did you have a question?
Go ahead.
Okay, So this is important to recognize because if you consider these two program or approaches side by side, specialization requires a lot of knowledge, right? You have to know how the language works, but also you have to know all the optimizations the compiler is going to be applying, and you have to even know what order those optimizations are going to be in. And so using the specialization approach requires a lot of repeated manual implementation because this means that you have to make a different translation validator, not only for each compiler you're validating, but also for each configuration of the compiler you're validating. Whereas with equality saturation, all we had to know were the basic axioms about these language, and we were able to take care of the rest entirely on our own. And what's particularly important is that equality saturation can even validate optimizations it's never seen before. And this will be important for this next application I'll be going into. But.
Question on the previous chart.
Yeah.
Are each one of those percentages, is that referring to a series of optimizations that are all done together and then validated, or individual optimizations that are validated?
This is method in, method out, how many methods we're able to do. So there could have been many optimizations. And usually that's what gets messed up is when too many optimizations happen and some important intermediate state gets lost. That sort of tends to cause the whole hole that goes on. So if there's a train that doesn't sort of like erase some past information, then it tends to be fine. But if it erases past information, we and basically all the other approaches that we know about get stuck at some point.
And how did you select which optimizations were validated?
We turned on everything intra-procedural. So as I said, they actually some of these are because they actually use inter-procedural information as well. So that's just something we can't do anything about without somehow changing LLVM. So this is run inter-procedurally, and then we validated what we could.
So question.
Yeah.
So my understanding of translation validation is that the queries to the theorem provers are usually very simple once you infer the simulation relations, right? Whereas in your case, you're constructing this key graph where you're introducing new nodes on fly, right? So is there a danger of sort of getting into a loop where you keep adding nodes to the graph?
Yeah. So for our thing, it doesn't necessarily terminate always. In our practice, we've had it so that, or in practice, if there are no loops in the thing, then we will terminate. But if there are loops, then one of our basic axioms, actually, I'll be getting to later on, will guarantee that it won't terminate. So we found a depth first, because there's just infinite number of options at that point. And so what we found is that a breadth first search through expressions works much better than depth first search because it sort of prevents you from going down a rat hole. Make sure that you try your options broadly rather than getting, okay, go through this loop, okay, keep going through the loop, keep going through the loop. We don't get stuck into that kind of trap.
But even without loop, I'm thinking if you add arithmetic expressions, you can create an infinite chain of arithmetic expressions, right?
One of the big things is that our stuff will reuse nodes as much as possible. So I'll see some more of that later on. But even if you put the axioms for like associativity and commutativity, that's like a huge blow up in the number of expressions that are equivalent, but a representation that's actually quite compactly represented, all those equivalent expressions. So yes, there's a wide variety, but because we have this sort of additive approach and because we reuse things and say, here's an equivalence, and we have this nice locality aspect of it, right? You can reuse sub-expressions a lot. It tends to actually not blow up in our representation until we start adding loops.
Can you explain the difference between all and opt columns again?
So this is all we're considering all methods, and we're only considering the methods where the optimizer actually made a change. So lots of times the optimizer doesn't just says input output can't do anything, and so this is just the only considering optimized ones.
I see. And what was the proportion of the 1864 functions that were actually changed? Can I tell that from this graph, from this table?
I don't know it.
Okay.
Looking at the numbers, I'd say it's not huge, but yeah, so unfortunately, I don't know it. Any more questions before I go on? Yeah.
So your conjecture is that all the failures are because of inter-procedural?
No, not all the failures. Like talking with other people who've worked in this area and stuff like that, things that come up are basically too many optimizations have been applied, it's a good thing that a lot of optimizations have been applied, but it's done so in a way that somehow some important intermediate state got lost, and we can't figure out that intermediate state that connects the two sides together. So as you saw, often you sort of drift from one side into the other side, and you converge in the middle. But if something has been done that makes that middle state just not there anymore, we can't figure it out, and basically everybody seems to get stuck in that situation. good to go. So so with this approach now, with translation validation, we're making it so that companies can actually use a compiler or use an optimizer, even though it's unreliable, but still safely do it with translation validation. And after doing that, I worked on making it so we can actually extend optimizers with new optimizations and make this accessible for typical programmers. And the reason why I thought this was important was that back in my industry days, what I remember having to do was a lot of optimization by hand. I'd write some program like this, an image processing program here, and I'd realize that this I times 50 plus j isn't really the best way to access this image. Rather, we could be doing image plus plus in order to get rid of that multiplication from inside the loop. And so once I've recognized this, I have to have this choice to make between this, keeping around this program that's easier to understand, not only for me, but more importantly for my coworkers, and this other program that will execute more efficiently. And this choice comes up a lot because many optimizers, including GCC03, won't actually perform this optimization. And so if you're running an image processing, you've probably run into a situation, and you may have thought, okay, well, why don't I extend the compiler in order to take care of this optimization for me, so that way I can keep around this intuitive code, but execute this more efficient code. And let's consider how much work is involved in that. Well, if you're so fortunate that the optimizer actually is open source, well, then what you have to do is check out a copy of the source code, learn the architecture of the optimizer, and then implement your optimization, even though you were doing image processing, so you may not be aware of programming language techniques. Then you have to integrate that into the pipeline and compile your new compiler, distribute to your coworkers. But before you do that, you should make sure to debug your implementations, since after all, we just talked about how compiler bugs can be quite annoying, and you don't want to be guilty of those. And then you have to deal with the fact that this compiler you just checked out is going to be being upgraded by the community as well, so you have to merge all those upgrades with your changes in order to make sure your team has an updated compiler. And so you can see this is quite an intimidating amount of work that scares off a lot of programmers, including myself. And so in light of this, what I did was make a trainable optimizer. And for this, in order to extend it with that optimization I showed you, all you have to do is give a single example of the optimization. In fact, that example I just showed you works just fine. And from that alone, it will take care of the rest for you. And there's a little catch to this, though, which is that, sure, I could learn this exact optimization here, right? But how often are you going to be writing programs that work on 50 by 50 images? Not that often. So really what you intend me to learn is some more general version of this optimization, one that would work for any W, any H, and any use of image I times H plus J, and change this into use of image plus plus. And furthermore, you'd want me to learn a valid optimization, one that doesn't introduce any bugs, and so you hope I learn side conditions like this H has to be loop invariant, and this use can't modify IJ or image. Now, recognizing that this is really your intent, oh yeah.
And it's only if you want.
What?
Like, you know, the image, if you do image plus plus, it appears like
yeah.
Use, right?
True.
Use,
yeah, there's many more side conditions, which is why we don't want people to have to deal with this. So recognizing this intent, what I did is make a system that will take this concrete example and automatically figure out how to generalize it into this more broadly applicable form. And the insight I had for doing that was that this optimization you gave us here needs to be correct. Otherwise, we don't want to learn it. And so in particular, these two programs need to be equivalent. So if we can understand why these two programs are equivalent, we can understand why this optimization works and how we can go about generalizing it. And so with that, we made up an architecture for a trainable optimizer. And we assume that the programmer gives us these two snapshots of the program before and after, for which they want us to infer the optimization that they implied. And what we do is we hand these off to a translation validator, which not only makes sure the programmer didn't make any mistake in these optimizations, but also gives us a proof these two programs are actually equivalent. And this proof is important because within it, we can determine what details of the programs are important and which ones aren't important and can be generalized. And so by generalizing this proof, you can actually get generalized versions of the input and output programs, giving us a generalized optimization for which the original one given to us by the programmer is just a concrete instance. And so with this architecture, what we enable is a way to teach, or is a way to enable programmers to teach compilers broadly applicable optimizations that are guaranteed to be correct by writing just one example of the optimization being applied, written in the language that they already know rather than some compiler-specific optimization. And so, at least I believe this makes extensibility very accessible to a typical programmer. Now, to get some more detailed understanding of how this actually works, let's say this programmer knows I'm giving her a presentation and says, Ross, please learn that 8 plus 8 minus 8 can be transformed to 8. And so I'd say, OK, well, I'm going to hand these off to a translation validator, which is going to prove that 8 plus 8 minus 8 actually equals 8. And then we want to generalize this proof, but before we do that, we have to look inside the proof. And so let's take a look at what this translation validator actually does. So the translation validator really starts off knowing absolutely nothing about the equivalences of these two programs, right? Really all it knows is properties about the overall language it's working with. So it knows, for example, that anything minus itself equals 0. And it can use this fact to infer that 8 minus 8 equals 0. And so as it runs, it's going to construct a proof of this database. In particular, it's going to say that implying this axiom, we could add fact 1 to this database. We also know that if something equals 0, then anything plus that equals itself. And so using this axiom and this fact, we can infer that 8 plus 8 minus 8 has to equal 8. And again, we make a note that by using fact 1 and applying this axiom, we're able to add fact 2 to the database. And this fact 2 is important because it actually proves that this translation or transformation given to us by the programmer is in fact valid.
You also use associativity. You use this associativity.
Oh, yeah, I guess I'm sort of assuming that there's parentheses there. So if the parentheses are there, then we're not assuming associativity. But yes, that's another axiom we can add on. Sorry, going back. Oh, yeah, so we just proved that this translation given to us by the programmer is correct. And so we can move on to proof generalization. Now, the thing I found out is that proof generalization actually works best by going backwards to the proof. So I'm going to be going from right to left. And to see how this works, I'm going to move these axioms out of my way. And I'm going to start off with some general program A transforms to some general program B. And I want this to be valid, and so I need to prove that A equals B. And the way I'm going to go about doing that is I'm going to look at this concrete proof here to figure out how I can refine A and B so that they actually are equivalent. As I do so, I'm going to maintain the invariant that this is the most general program transformation for which the portion of the proof that I processed so far applies. Since I haven't processed any of the proofs so far, I start off with the most general program transformation. Now, to start refining things, as I said, it works best by going backwards. So we're going to look at the last axiom that we applied, this one here. In order to have applied this, that means there had to be some C and D, so we knew C equals 0, and then we use that to infer that D plus C has to equal D. And so we can look at our concrete proof to see how we use this. In particular, our proof tells us that we apply this axiom using fact 1. And so C equals 0 has to be fact 1. And so we can add that to our databases as a future goal to prove. Similarly, our proof also tells us that applying this axiom, we added fact 2. And so D plus C equals D has to be fact 2. But this time, we already have a fact 2, namely A equals B. And so to reconcile these differences, what we do is we can unify these two facts. We can take all the uses of A and replace them with D plus C. And we can take all the uses of B and replace them with D. And after doing so, it actually makes complete sense to transcribe our notes from below to above. From below to above. After all, if you use this fact 1, you can get that fact 2. And note that when I was making that substitution, I also made the substitution within the generalized transformation. And so I restored the invariant. This is the most general transformation for which the portion of the proof that I processed so far applies. In particular, if I can figure out how to refine C so that it actually equals 0, then that transformation will be correct. So to go about doing that, again, as I said, we're going backwards. So we're going to look at the previous axiom that I applied, this one here. And in order to do this, there had to be some E, such that we inferred that E minus E equals 0. Now, this axiom makes no assumptions. And so we can start off with the empty database. This is what you'd expect from a good proof. And then we can look at our notes to see that in applying this axiom, we add to fact 1. So E minus E equals 0 has to be fact 1. But once again, we already have a fact 1, namely C equals 0. And so once again, we reconcile these differences by unifying these two facts. In particular, by taking all the uses of C and replacing them with E minus E. And once we've done this, we can transcribe our notes again and say, well, if you add fact 1, or you can apply this axiom to add fact 1 to the database. And in so doing, what I've just built is a generalized proof that this generalized transformation over there, D plus E minus E transformed to E, or to D, is in fact valid. And our original concrete proof and concrete transformation are just an instance of this generalization by taking all the uses of D and E and replacing them with 8. So by understanding why this transformation given to us by the programmer is in fact valid, we're able to learn a more broadly applicable optimization. In particular, by examining the proof of equivalence of these two programs, we're able to learn optimization from the programmer. And so to recap what I did at a higher level, I hand these two programs off to a translation validator, which gave us this proof that they're equivalent. And this proof said, or proof works because these two weights are the same and because these two weights are the same. And so when we hand this proof off to the proof generalizer, it then inferred, or it maintained those equivalences in the generalized transformation. However, the proof didn't need all four weights to be the same, and so we could use two different symbols, D and E, in the generalized transformation. And what I proved is that using this process, we'll always learn the most general optimization for which is a proof of validity. And so with a strong guarantee, we're able to learn a wide variety of optimizations from just single examples of them being applied. And this interloop strength and bound reduction is in fact that image processing or optimization I showed you earlier.
So do you use, like, when you try to prove this equivalence, you use the technique you just described, like pegs again?
It uses, so these all, like, lots of these have loops and stuff, and so if we want to do loops, then we have to use pegs, and same with, if there's anything with side effects, you have to use pegs. So what I showed you was a very...
That's all cool, of course. Yeah, if you have load and source, so you use the same techniques.
Yeah. So we're building off this equality saturation kind of approach. So underneath, to make that technique I showed you actually work for realistic programs, then we use pegs and equality saturation on top of everything. And so here, so the cool thing is with this approach, and the fact that our technique actually can generalize to other representations as well. What this does, it tells us that since we build off translation validation, as the technology for translation validation improves, so will our ability to learn new optimizations from programmers.
What's the factoring and distribution?
It's things like putting the multiplication inside the loop and to get rid of. Sometimes you can put a multiplication inside the loop to actually get rid of it by distributing it through everything, and other times it's better to factor it out and put it at the end of the loop. So that's just sort of moving operations into and out of a loop.
So can you, or how hard would it be to do something like loop interchange or loop unrolling? Unrolling should work, right?
Well, so by unrolling, do you mean the one where you take the loop and then make sort of double copies of it, or do you mean the one where you pull out one iteration of the loop?
That latter one's called peeling.
Okay. So some people use the latter unrolling for the latter one too. So that's why I asked. Okay, so the other one, we actually haven't done that because basically our representation, I was showing you earlier or later on, sort of has iterations kind of tied into the semantics of it all. So we have looked into ways to get rid of that. We figured out you can do sort of meta operators that allow loop unrolling, but we haven't actually tried putting that into practice. Loop peeling is easy, and I'm feeling like
something like loop interchange.
Oh, and loop interchange actually.
Dependence testing to prove it correct. It's probably beyond the proof system at this point.
So loop interchange, it depends on exactly how they're bundled. So if you can figure out, often what we'll do is if we do our alias analysis ahead of time in order to figure out how to turn it into a peg better, and in that case we'll actually get these two loops to actually be completely separate expressions. And so loop interchange is extremely easy to do in that situation because they're actually already separated. In other situations it's much more difficult because you have to figure out sort of figure out after the fact that they can be separatable, and it's a little harder to do. Sometimes we can do it, sometimes we can't. And so compared with bisimulation relation, like bisimulation relation can do things like loop unrolling better, but loop peel or loop interchange they have a terrible time with. So there's some pros and cons to the two different approaches. And what's interesting is that the two different approaches seem to have the same walls I was talking about earlier in the translation validation. So again, because this works out translation validation, if we use a bisimulation relation translation validator, then things like loop unrolling would be just fine. But here, since we're using our quality saturation approach, things like unrolling are difficult, but loop interchange is better.
So how does this work practically? I mean, if you can do this, why have all this code in a normal compiler, handwritten, that implements these different optimizations?
So what there's sort of a detail here, which is that, as I said, there's the most general optimization for which this works. But what does generality mean? And so in our situation, we formalize what generality means, and depends on the logic that you're working with for that proof. And so generally for this process, you need sort of a first order logic to do all this stuff. And so when you implement optimizations by hand, you can basically do things that require higher order logics. And so there's some optimizations that are better done by hand because they actually will work to more broader situations. But the reason you don't want to do that all the time is because there's a lot of optimizations that are only going to be useful for certain domains, and so you really only want to learn, like if someone is in that domain, then they'll say, okay, learn this optimization and have it there. So I wouldn't say you should go all the way this way, and I wouldn't say you should go all the other way. Really, it's a matter of balancing the two.
Do you have performance results? Are you going to show this?
I have performance results for optimization later on. The issues that come with performance for optimization, well, part of it was that because we chose LLVM and Java or bytecode, that they're a little too high level for a lot of things. So if you can find some programs that have some key bottlenecks, and you actually put these optimizations in, then you'll get good performance results. The issue is there a bottleneck in the code that's actually something that you can optimize? If there isn't, which is often the case, then you're not going to get big performance results. So there's a big issue with evaluating optimization in general. So I can go into more details about this whole optimization evaluation problem I found out when I started doing this research. But later on, I'll actually show you some success we had with the ray tracer where there was a big bottleneck, and it had to do with these kinds of optimizations. Okay. So now they made so that we can extend the compiler with new optimizations by just giving an example. Another thing I've looked into is making it so we can infer optimizations entirely automatically, well, given the properties of the language. The reason why I found this to be important was that when you make a new language, optimization tends to be a big hurdle in order to get the language adopted. And you might wonder, well, there aren't that many languages being made every year. But in fact, many companies, like the old video game companies I worked with, actually have their own in-house language that's maintained by a single person who would really like to have an optimizer but doesn't have time to implement an optimizer. And so this technology would benefit them. And also domain-specific languages are becoming more and more common. And so by incorporating my technology, you could learn domain-specific optimizations for those domain-specific languages. And so to see how this works, I'm going to sort of focus on one very classic optimization known as loop induction variable strength reduction. And what this does is it takes this program here, and it translates it into this program over here, and particularly gets rid of that multiplication from inside the loop. And the way it goes about doing that is it says, OK, well, this 4 times I is going to turn this loop variable j. And to accommodate that change, I'm going to change the increment by 1 to an increment by 4, and I'm going to change the bound of 10 to a bound of 40. And the reason why you might typically would go about doing this is because it's very useful for things like array optimizations, where typically this 4 times is like the size of the array elements, and so you want to get rid of that multiplication from inside the loop. And so if you were to go through the effort of actually implementing this optimization for your language, well, then there's still one more subtle issue you have to deal with, which is called phase ordering. And the issue is that you can start off this program here, and sure, you can apply loop induction variable strength reduction in order to get this ideal version here. But you're also going to be writing a number of other optimizations, such as the fact that 4 times could be replaced with left shift by 2. And if you apply those optimizations first, well, then they'll block out this loop induction variable strength optimization, in particular because they get rid of this multiplication from inside the loop. And so this issue of optimizations sort of conflicting with each other causes what's known as the phase ordering problem. And so recognizing this, let's consider how much work is involved in implementing an optimization for your language. Well, with the traditional techniques, what you do is first identify all the multiplications inside the loop, and then filter out all the non-inductive cases, that is, variables being modified in some way besides incrementing. Then you decide which of the remaining cases you want to actually optimize, because if you do too many of them, you'll overflow or overload your registers. And then you have to add a new loop variable for each of the remaining cases and insert the appropriate increments for each of the remaining cases and then replace the appropriate multiplications with the appropriate loop variables. And so once you've done all this, you have to integrate your optimization into your pipeline and addressing that phase ordering issue. And then you have to make sure to debug everything because there's a lot of little things that can go wrong here. And again, we don't want to introduce compiler bugs because they're very painful. And so you have to do all this process basically for each kind of optimization you do. And so this approach requires a lot of repeated manual implementation. And so in light of that, I figured out a way to apply equality saturation to this problem. And in particular, with my approach, all I have to do to get loop induction variable strength reduction is teach us 3 basic axioms about your language. Distributivity, 0, and identity. And from that alone, we'll be able to learn loop induction variable strength reduction automatically. More generally, it helps us if you also give us sort of estimates of what your operators cost in order so that we know how to prioritize them. And then once you've done that, we can automatically infer a large variety of optimizations, all of which are guaranteed to be correct because we'll actually be able to output a proof that the transformed program is equivalent to the original program. And so you don't have to worry about this debugging problem here. And so to see how our approach works, we start off with some control flow graph, right? The standard representation for imperative programs. And again, this isn't very good for axiomatic reasoning, so we're going to translate it to our own representation, the program expression graph that I talked about earlier. And once we have this nice mathematical representation, well, then we can move on to equality saturation and infer a bunch of equivalent ways to represent this same program by applying those algebraic identities. And once we have all these equivalent representations, well, then we can incorporate what we call a global probability heuristic, which analyzes all these equivalent optimizations and picks out what's the optimal one according to the cost model that you gave us. And once we have this optimal choice, well, then we convert it back to a control flow graph in order to get the standard representation that we can move on to other stages of the compiler, like lowering down the assembly level. Now, to see how this works in some more detail, let's consider this loop induction variable strength reduction example I showed you earlier. And there's a new challenge here, which is that this comes in the form of control flow graph. But again, I said control flow graphs aren't very good for this kind of axiomatic reasoning. And so we want to figure out how to represent this as an expression. And the issue is that this program has a loop in it. And this loop really represents an infinite number of values. So how do we represent an infinite number of values as a finite expression? And so to solve this problem, the idea I came up with was to use expressions with loops in them themselves, essentially recursive expressions. And so this 4 times I loop value here we represent as this expression over here. In particular, we have this theta node that says that loop variable I starts off at 0 and is incremented by 1 in each iteration of the loop. And so once we have this nice loop representation, or a nice mathematical representation of this loop, we can move on to the familiar quality saturation process that we talked about earlier. So we can apply an axiom, say the fact that left shifting by 2 is the same thing as multiplying by 4, and so we can add this equivalent representation here. And note that once again, we're adding information. We're not throwing away the original control flow graph. And so this is very different from the prior approaches. In particular, it's additive. And this is how we deal with that phase ordering problem, because we're still free to explore in another direction. Particularly, we can apply another axiom that says that any operator distributes through our theta nodes. And this results in this multiplication of additions here, which then allows us to apply distributivity. And that results in this 4 times theta node here. And there's already a 4 times theta node over here. And so we can reuse that same node in order to keep our representation nice and compact. After doing that, we can apply zero and identity in order to simplify those expressions. Then what we've just built here is what we call an EPEG, or an equivalence program expression graph. And what this does is it has all these sort of equivalent classes of values here, and it says that here's a bunch of equivalent ways to represent these various subcomponents of this program. And so once we have all these equivalent options, well, then we can incorporate a global property heuristic to tell us which of these options is, in fact, the best one. And so it'll analyze this EPEG in order to figure out one representation for each equivalence class that optimizes the cost model that you gave us. Now, once we have this, we can simplify it down to a program expression graph, and this gives us sort of our optimized result. And lastly, I translate this back into a control flow graph. And so this corresponds to this graph here. In particular, it says that there's a loop variable, j, that starts off at 0 and is incremented by 4 in each iteration of the loop. Yeah?
I didn't see the 10 and the 40 coming up.
Yeah. So sorry, I just focus on this thing here. That you start adding less than the 40 bits, start going into a much bigger picture.
Oh, it would distribute, and then like you would at a certain point say that.
Yeah. You have an axiom that says that it's
10 would be smaller than 40. 4 times the thing would be smaller than 40.
Yeah.
Okay.
So you have to, this is where you also have to know that the upper bound is small enough to make sure there's no overflow and stuff like that. So all the axioms I showed you so far actually hold for modular arithmetic. So they're not an issue, but things like inequality axioms, the standard ones don't hold for modular to make sure that the bounds are appropriate.
So is this representation just static single assignment, or is it different from that?
It's a more complete form of it. So it's actually one that, so static single assignment, you can't throw away the CFG. There's not enough information. Values that are different actually will get conflated. And gated SSA, you can consider this sort of as very similar to a version of gated SSA where all loop indices here are explicit. There's versions that don't have explicit loop indices, but you can't throw away the CFG because they'll actually merge values again that are not the same. So this is sort of one that's been fleshed out all the way to make it so completely independent from the control flow graph. And so we figured out how to way to actually convert from this representation back into control flow graphs. We also gave it denotational semantics showed that gave a transformation, and we proved in Coq that moving from two representation actually preserves semantics. So it's sort of a very thoroughly done SSA, but along the same lines.
But you do have this challenge of reasoning about loops the way people reason about loops in the control flow graph. Is that right or no? In other words, the kind of optimizations that Catherine was talking about earlier, if it's in this form, then how do you reason about those or those?
So this is one. So if you had another loop down here, say, and if so, they're effect-less loops, this becomes much easier because actually in our thing they'll just be one loop expression, another loop expression. They won't even be in any sequence on top of each other. And so that's where some things get much easier. When there's an effect going through, then that forces them to be sequentialized, and that gets things a little messier.
Can you still reason about them and do the kind of optimizations that you would want to do?
We've had mixed luck on that one, so it depends on just how complicated the story is. So if the story is simple enough, it works out. If it's too complicated, then we at least automatically we haven't been able to do it. Not automatically, we can do it by hand, and that's another thing. More questions?
So actually, you haven't said anything about inlining. So is it just totally trivial, or is there some subtleties about it that are difficult to understand?
So I've been talking about axioms here, but really our engine actually allows arbitrary, what we call equality analysis to come in, and they'll do fancier things. And so one of them is an inliner. And so it'll say, okay, here's things that are have been approved for inlining because they're just use some inline heuristic or whatever, and then we'll inline them. And it's fairly standard how inlining works: is add the equivalence, or the equivalence between the function call and the function call replaced with all the expressions, or with all the expressions replaced. Some things we found. So it's very important to get rid of intermediate variables. We found things that try to do lambdas within the thing. It's possible to do, but in practice, because of the sort of exponential kind of exploration, this additive approach, it just becomes very, very messy when you actually try to use lambdas and try to do stuff like substitute this inside the lambda. It doesn't work very well. So lack of intermediate variables is actually a big thing towards getting this approach to work. Okay, yeah?
You've described the general scheme, but I'm curious, would you consider optimizations like skipping the iteration where j is 0, or going backwards so you can compare with 0 instead of 40, or replacing the whole thing with return 180? Or...
So we have the first one is easy. The first one we can do. Actually, that one will just happen automatically. Plenty. That's the loop peeling thing. The going backwards one is not easy. So that one I wouldn't. That one requires you to know. So basically, we represent these as sort of this theta node is this is where the iteration thing comes in. It's right. It says, okay, iteration 0, it's 0. Iteration 1, it's 4 plus what it is at iteration 0. So our sort of semantics, our representation incorporates iteration count into it. So if the little shifts are fine, but things like reversal, but you can't even reverse an infinite sequence, right? So you really have to know reversal with respect to some maximum point. And similarly, sort of taking every other one you can do, we have sort of an evens and odds thing. That's how you get the loop peeling or the loop unrolling thing. But we haven't tried putting that in practice. So some loop things, no problem. Other loop things, difficult. I guess Ben was up first.
So this is a totally off the wall question. So you know about Denali, the super optimized?
Yeah.
Okay, so is this, how close is it?
So Denali, they're basically very similar strategies, this kind of equality saturation thing. Denali is within a block. And within that block, having just a single block very much changes the picture of things. So you can use very different techniques for doing this process. And you can, basically they work on things like 6 instructions at a time. So the scale of things is completely different. So we're doing whole Java methods at a time, or whole C methods at a time. And so they don't have to worry about loops and stuff like that. So I really view them as, this is more meant to be the generic purpose compiler, or smart generic purpose compiler, whereas Denali is here is a small chunk of 6 assembly instructions that need to be optimized to all hell, and go through it as detailed as possible.
How much of the state space you explore, right, in terms of the possible?
So they have finite state space, right? So they actually explore the entire state space.
Right.
So that's why they can use a SAT solver in order to actually say, is this true or not true? Whereas we can't, because our state space is infinite. So that's why the depth or the breadth first search is important rather than doing depth first search, because we can't explore the whole space. Or sorry, Manuel first.
So look, this is a very structured loop. So you're saying you can translate CFGs to pegs. So does that work for any CFG?
It's the, oh no, I forgot the term.
Reducible.
Yes, reducible. Thank you. Reducible CFGs we can do, and there's a way to translate irreducible CFGs to reducible CFGs with some duplication. But any reducible one we can handle. And in fact, something that took a lot of struggling, a suffering month, was figuring out how to make loops that came from non-structured loops and still revert them back into non-structured loops. So if they had breaks and continues, actually restore them to a loop that still has breaks and continues rather than it has a lot of duplication and unwanted branches. So that was messy, but it's been figured out.
And in terms of these loop induction terms, do you have to figure those out ahead of time, or they just fall out of?
These things just happen, right? A lot of the optimizations were let's just see what happens, and we threw them in, and they worked. just from the axioms. And some of them they didn't work, and it's because either because there's sometimes it's because there's just like something big like reversing the loop is just doesn't really work with this kind of representation. And other times it's because we're missing an axiom, so we just add that axiom and we get it. So like the interloop strength and bound reduction axiom actually requires something the long line what you mentioned is like basically at the end of this loop we know that J is 40, right? And so this actually has that, knowing that fact requires sort of a higher order axiom, and so we added the higher order axiom into the system, and then we could do some fancier stuff that way. So something I've learned in general, which has come up a few times, is that the representation you choose for optimization is a big factor as to what kind of optimizations are easy to do and are not easy to do. And so, I chose this one here, but there's many other ones that could be valid for different kinds of programs and different kinds of things. And part of that proof generalization process, actually, I made sure that the algorithm I came up with actually could be generalized to other kinds of representations as well. So it's not just stuck with pegs; it can work with other kinds of programs.
So this is obviously fairly akin to program verification technique, the techniques it uses. Usually in program verification, when you have loops, you summarize them via a loop invariant. And there's a variety of techniques for inferring loop invariants. Mm-hmm. I was wondering whether you think you have all the power you need, or if you were to apply loop invariant inference techniques and incorporate that into your technique somehow, would you get more?
So what we found is we actually already have in our say the anti-aliasing, there's a few things that are best done before you start doing optimizations in order to basically learn loop invariants. And because the reason is because it's hard. Sometimes it's possible, but it's hard to do loop invariants dynamically because you have all these equivalent representations, and you're basically trying to do induction over these equivalent representations. And so it doesn't really work very well, we found out in practice. So we'll do loop invariants beforehand, and then we use those ones. And once we have a few beforehand, we can figure out how to augment them dynamically as well. But we still need some, we found that we need some starting point to go from in order to get those. All right, all good? Okay, so now to look, we've probably seen this, but looking back where we came from, it started off as 4 times I, it got changed to j, and had this increment by 1, and changed it to increment by 4, made this bound of 10 and changed it to bound of 40. And this looks familiar because this is in fact loop induction variable strength reduction. And what's cool is that I didn't program this optimization explicitly, right? It just sort of happened. And we call this emergent optimization, and we found that there are many optimizations that would emerge just from these basic axioms automatically. And so this is how we're able to get sort of a language optimizer and automatically infer optimizations. Now, I've been talking about language sort of optimizations here, but we actually found out that we could also apply this to libraries. And the reason why this sort of came to me as something important is that I remember back in my undergraduate days, I had to write a ray tracer, and I had this choice between mutable vectors and immutable vectors. Now, mutable vectors meant I had to write big sequence of commands like this in order to implement this very basic expression with immutable vectors. Furthermore, mutable vectors, if I chose them, meant that my code would be error prone because I had to track things like ownership, make sure that the wrong person doesn't modify the wrong vector at the wrong time. And with immutable vectors, right, they don't have those kinds of problems. And so in light of that, you might expect me to choose immutable vectors. However, I was worried that immutable vectors would be inefficient. In particular, even this basic expression here allocates a number of intermediate objects. And that is objects that are just made and then thrown away almost immediately. And so because of this, I decided to go with mutable vectors in order to get better performance. And I remember this decision years later when I started working on optimization. And so what I did to see whether I could apply my optimization techniques to this library design, I went back to that ray tracer and re-implemented it to use immutable vectors the way I would have liked to have implemented. And I did find out that actually ran 7% slower. So I was justified in my performance concerns. And so what I wanted to do is apply my techniques in order to replace these sort of very manually intensive library modules and get these sort of nicer ones that and still have the same performance guarantees as these manual ones. So the idea I had was that using my techniques, what I could enable is library usage optimizations. In particular, I had the idea that we could express the various guarantees that we have about using your library as axioms. So for example, if I had a vector library that has these adds these two vectors together and gets the first component, well, that first component is going to be the same thing as getting the two vectors first components and summing them together. And so once we incorporate all these axioms into this quality saturation process, then we'll automatically infer optimizations for using my library, specialized for using my library. And so I applied this to that translation, to that ray tracer, and was actually able to get immutable vectors to run faster than the mutable vectors because they were more axiom friendly. In particular, the optimizations we learned were able to reduce the number of allocations by 40% and get rid of all those intermediate objects. And so by using this technology, you can make it so that you can design your libraries the way you'd like to and still get the performance concerns or performance issues by taking advantage of these axioms. And this
DTH Zurich who does this axiomatic rewriting-based approach to DSLs, right, for compiling high-level specifications of things like fast Fourier transform down to low-level code which ships in Intel libraries. So I take it rewriting is strictly more powerful, right?
So this for one thing, this is within the same language. So we're optimizing. So like we take Java code and we rewrote it to Java code. And so we don't. So this is a performance on top of not even having to worry about lowering down. And there's actually also all these metrics I showed you or showing you are on top of the JVM's optimizations as well. So this is optimization the JVM couldn't do, and the JVM optimizer actually is fairly advanced. We found out.
Sure. So, but I'm just thinking of it, I'm just thinking in terms of comparison to a rewriting system. So what is the expressiveness of the things you can rewrite?
Well, so we can, rewriting system, this is essentially a kind, you can think of it as a rewriting system, but with this, that global profitability heuristic, which allows you to explore many rewriting simultaneously. Whereas with a typical rewriting system, you have to worry about only, like, it basically has the phase ordering problem. If you rewrite things in the wrong order, you get problems. And so we've sort of addressed that issue by using the quality saturation, keeping this additive approach, and also we figured out how to extend it to loops and stuff. Sound good? All right. So
there's also, I'm sorry, it's just that the whole idea here is ringing a lot of bells. There's like Pingali's stuff, right? All about abstract data types and sort of doing higher level transforms. It seems quite related to,
I'm not familiar with the work, so it could be.
Right. Essentially, the idea is if you have sort of, if you have some knowledge of the higher level semantics of your data structures, you can do commutativity, things like these. You can do optimizations at a higher level. So I just wonder how it compares to something.
Yeah, so in general, basically, the cool thing is that we figured out that, or we did the experiments to show that actually makes a difference. We can do that stuff automatically, right? We don't have to. All we have to know is the axioms, as you're saying, and at least my intent with all this is to make it so that people can actually program differently, not just like take existing programs and run them and get them faster, but actually make it so people can write their libraries in a way that's nicer. So this at least substantiates that would work.
Trusting essentially the pragmas or whatever the immutability.
We're trusting the axioms are correct.
That's right. So, but you're inferring them from the type signatures?
No. So I'd written the library, so I just went through and said, okay, here's some axioms that I imagine would be useful, and then said, okay, infer optimizations. So the library writer would provide axioms. We can't infer them automatically. In fact, ideally.
It wasn't so much about the axioms. It was really about the purity, like knowing that the function was pure and that.
Again, so that'd be an axiom. Like the reason why I like the axiom thing is that it means you don't have to have the library code.
Yep.
And so particularly with OO systems where you're dealing with interfaces.
Okay, but you're not addressing the problem of checking the code against the axiom.
No, so that is a whole nother story. Yeah.
Does the library writer also have to write cost functions?
We didn't have them do that, no. We have our cost model is actually very naive, but we found out that naive cost models actually work pretty well. It would be better, actually the one thing where it would be better though, in practice, is knowing that some methods are more sensitive than other ones. So right now, it's just treat all calls uniformly. And really it'd be better to say like, no, call that function is nothing like calling this function. Please, do more of these ones and less of these ones. But we didn't actually do that in our system. The techniques we use can accommodate that, but for the amount of automation we're trying to go for, there wasn't something we could go for. All right. So we've been talking about performance, but I haven't really talked about the performance of my own tool, right? So, sorry?
So don't you have to worry about aliasing in the last approach? I mean, when you rewrite access to the new object, if there are aliases of that, you might want to rewrite them, or I don't know.
Oh, so...
so do you syntactically rewrite objects, or do you...
We're not rewriting objects or anything. We're just rewriting code. So here, I mean, here you'd still have U and B would still stay around. It'd just be this thing. So we don't have to worry about aliasing or anything like that for the optimizations that we're dealing with here. The only things that the things where aliasing was useful is knowing when that stateful operations can commute. And basically, almost all the time that aliasing was useful was knowing that stateful operations would commute. So aliasing isn't really too big a deal for these kind of library axioms. Okay, so going on to performance, this is sort of that tool chain I showed you in the various stages of the compiler. And so to evaluate how effective this tool chain was, how efficient it was, we ran this on the SpecGAVM 2006 benchmark suite. And what we found out was that equality saturation actually runs quite quickly. The slow part is actually global probability heuristic. And to figure out why, we did some investigations, and we found out that equality saturation is actually doing such a good job that even though we stopped it off early, by the time we stopped it off, we would find a trillion ways to represent a single method on average. So you can imagine it takes a while to figure out the best option out of a trillion options. And so that's why the global probability heuristic takes a while. Now, in light of the fact that even though there's good reason this takes a while, we still want to figure out a way how to get over this hurdle, right, in order to get this technology adopted. And so the idea of combining this technology with the previous technologies I showed you earlier in order to speed up optimization in general. So this technique I'm going to show you works for really any advanced optimizer, not just our own. And there's a lot of these things out there, such as Denali. And these things are smart, but as a consequence, they're slow. And some of them are really slow, and you have a lot of code you want to compile, but you don't want to wait around forever. So the other things out there are things like rewriters, which are quick and efficient, but also rather naive. And so what we would like to have is the sort of ability to combine the intelligence of these advanced optimizers with the speed of these efficient rewriters. And so the idea I had for doing this was that I could take off just a piece of your code base and ship it off to the advanced optimizer in order to get a very well-optimized version of that code base. I could then ship that off to your optimization generalizer in order to learn optimizations from the advanced optimizer. And I'm going to tack on what we call a decomposer in order to break this proof of equivalence up into a bunch of little lemmas. And so from each of these lemmas, we learned a bunch of mini optimizations specialized to your code base, which we could then incorporate into our efficient rewriter and pass the rest of your code base through the rewriter using these lessons that we learned from this advanced optimizer. And to see whether this is effective or not, we ran this on that ray tracer I talked about earlier. And we found out that the rewriter was actually able to get produce the same high quality code as the advanced optimizer, just using these lessons we learned from the snippet from just part of the code base. And furthermore, is able to do so 18 times faster than the advanced optimizer. So significantly address that performance problem I talked about earlier. And so to recap, sort of made it so that we can infer optimizations automatically and efficiently. And overall, made it so we can actually use optimizers, take advantage of them, even though they're occasionally broken. Made it so that we can extend optimizers in order to address our sort of more domain-specific needs. And made it so that optimizers are available for new languages and also for library writers in designing their libraries. And so by continuing this line of research, what I'm hoping to do is make it so that discussions like this are no longer necessary. We can focus on the more important things like correctness. And something else, since this is job talk and all, something else to talk about is the fact that this is really only one line of my research. Another line of research I've done, actually here mostly, is type systems. In particular, thanks to Juan and Chris, I learned all about existential types for dealing with type assembly languages for C#. And well, Chris is working on is this operating system verb that's guaranteed to be memory safe. And the big issue is that they want to be able to take C# code either for things like the scheduler or for user programs and run them in their operating system. But C# code is memory safe, but compilers are broken. And so you want to infer types at the assembly level to make sure that even the assembly code was still memory safe. And so that's what I did here. And this got me introduced to existential types. I made this big category theoretic framework. And this turned out to be very useful for dealing with Java. Actually, my students found this out for me, that Java has all sorts of problems with wildcards. They had this piece of code that they're writing for my class project, and they were very frustrated because this code wasn't compiling, and they had no idea why. And I'd look at the code, and I found out that the code is actually correct. The type checker was broken. And so to investigate some further, and found out that wildcards in particular, Java just does not do a good job with. So I applied this existential framework because wildcards actually kind of existential type in order to prove the algorithms that Java is using for type checking, and also figure out how to refine the type system a bit and show that it's practical to do these refinements in order to make sure that the Java type system actually is decidable. Well, type argument inference we can't solve, but at least the rest of it, subtyping, basic things, subtyping wasn't known to be decidable before, so now it's decidable.
What happened there? I thought Bill Wadler was on top of all that stuff.
Wildcards are subtle.
That was after. When did wildcards come?
That was the Java 5. So generics, wildcards all came together.
Generics and wildcards came at the same time?
Yep.
No, generics came before wildcards.
And for Java, I'm saying they came at the same time.
They did.
Yep.
But the generic Java prototype.
Oh yeah.
Did not have the wildcards.
Right. Yeah.
Right.
So Wadler had nothing to do with the wildcard.
Yeah. Got it. That's what I thought. Yeah. Okay. Okay. Good.
There's good reason for wildcards and what they address. There's also some messinesses. So they definitely like with the Ceylon stuff. So I guess I'll go on to Ceylon.
Okay.
So Ceylon's there's this team at Red Hat working on making a new language. In particular, there are people who worked on the Hibernate project. If people familiar with that, they've had tons of years experience dealing with Java code, and they become very frustrated with some of Java's problems, like wildcards. And so what they want to do is sort of clean up Java and general OO enterprise programming. And so we're trying to learn all the lessons from these languages. So they're aiming for things like decidability. And so that's how my work got involved. We figured out that wildcards have some good aspects and have some weak aspects, or incorporating both of them, or trying to throw away the weak aspects and while incorporating the strong aspects, stuff like that. And so I've just been working with them on making sure the type system is nice and clean, has all these properties that they told me, so things like principal types they want, decidable types and decidable inference where they allow it, they want, stuff like that. So I've been helping them design their language and make everything look nice and pretty and meet their guidelines that they've given me. So this is sort of another line of research I've been doing, and then on sort of a longer term track, very, very far down the line, some problem I've seen is that if you have some tool for C#, well, you don't really know where that tool transfers over to Java. And similarly, if you have some cool proof for Java, you don't really know where that proof transfers over to C#. And this is frustrating because these languages, while they have some key differences, they also have a lot of similarities. And so you'd expect that a lot of tools and proofs can be transferred across these languages. But we don't really have a way of formalizing that. And so what I want to do is make a sort of a meta language for programming languages in which we can formalize requirements of tools and proofs and formalize properties of languages in order to make it so that one tool can transfer across many languages simultaneously. And similarly, to make it so that when you make a new language, you know what kind of properties you want to aim for in order to have access to the existing tools and proofs that have been made for other languages already out there. And I've done some work in this with effects here, and also looking into foundations of computation and mathematics, and looking into resource-constrained computation. So just sort of scoping the landscape right now. But I'd be happy to talk with any of you guys about that today or tomorrow. But at this point, I want to thank all the people I've had a chance to work with at UCSD and here. And, well, I guess thank all of you for the fellowship that let me do all this research, and then open up to any questions you may have. Did I talk too fast? Oh, sorry.
For your translation validation, why didn't you use an intermediate verification language?
What do you mean by that? Sorry.
Translate your. It seemed to me that you were building your own e-graphs and everything. So I mean, if you instead, let's say, translate into Boogie, then you get all of the transformations into formulas, and then you get the e-graph stuff from down below in Z3, for example.
Okay. Yeah. So we tried that. It didn't go very well. So this was also years ago, so this is when these technologies were younger, so it may actually work now. But the reason why we think it didn't work well is particularly because we had recursive expressions. And the algorithms that things like the e-graph solvers and stuff in Z3 and in Simplify and stuff like that don't seem to really like recursive expressions. They just run forever, go down a rabbit hole, and then you never hear back from them.
You mean because you say something in a quantifier somewhere, that's going to be instantiated?
It would do so that like we have that operation that distributes to the theta node. That can go on forever and ever and ever. And so we think that if we didn't have programs that didn't have that specific axiom or didn't have any loops in it, then it would be fine. So it didn't like those kind of things. So those are particularly kind of things that we wanted to actually have work.
So you wrote your own, quantifier instantiation?
Yeah. I used the read pattern matching algorithm I knew from undergrad. So, yeah. So that was how I got that to work. I guess
I had one more question.
Okay.
So there are like amazing results with the optimizer and stuff, and you actually ran it on like real Java bytecodes, right? So it's like a pretty realistic tool. But do you feel like like Ben Zorn was also asking, like, do you feel like I could really incorporate it in a Java compiler, for example? But is it practical enough?
I don't think it's ready for JIT compiling.
But say again.
I wouldn't say it's ready for JIT compiling. Actually, I think.
No, I was just saying, like, would I be able to build a compiler with no optimizer, right?
Oh, I see.
I'll just give it axioms and I integrate your framework.
There's certain optimizations that I wouldn't put in that class, because I mean this is rather high level. So things like register allocation, all those low level things don't really once you get this level of abstraction, you can't see the differences between those. So I wouldn't try doing those kinds of things in this system. Also, as you saw, there are performance problems. Actually, they're probably better now because it's years later and the solvers that we've used have probably gotten better. But actually, I think what would be better is rather sort of a compromise of systems. Take a traditional compiler that has many of the core things on there, add the extensibility aspect to them, and then make it so, particularly the strategy I showed you with the learning optimizations from the super optimizer, I think what would work best is running a super optimizer on your code base, say once a month. Learning all these axioms from it once a month, applying those for the rest of the month, and that way I've seen all these things. They'll have a much smaller set of axioms that run much more efficiently. And then another month later, after your code's changed enough, learn again and go again. I think that's a better approach towards going about this. It sort of accommodates those strengths and weaknesses of the system.
So I see that you have something about LLVM up there, and I was wondering if you could compare a little bit with the work on Vellum, which formalizes the LLVM intermediate representation, gives the semantics to it in Coq and so on. What kind of semantics do you use for LLVM?
We didn't. We didn't use the formal semantics for LLVM. So so Mike Stepp's the one who took care of all the LLVM specific stuff. So I did the general purpose kind of stuff. So he dealt with bytecodes and bitcode, bytecodes and bitcodes. And then he would talk to me when he'd run into some problem, like, okay, you can't figure out how to represent this, how to represent this, and then we talk about better ways to represent those kind of constructs and stuff. But overall, he was the more detail-oriented part of the project. So unfortunately, I can't go into the details of the LLVM thing.
So you had a translation from LLVM into your representation that you believe is faithful to LLVM semantics, and then you worked on your representation.
Yeah, and then we convert back to LLVM afterwards.
You needed to add the axioms, right?
Yeah, yes, we had the axioms. I mean, our translation from LLVM to our representation was very, very basic. It was here LLVM expression maps to this, it was very simple ones. So it's more the axioms are really the things that incorporate the semantics of LLVM. And they're mostly things like integer axioms and stuff like that. There was a bit of a mess with the fact that there's many different sizes of integers and all the other operations in LLVM are typed. And so getting all those to interact well with each other was a bit messy, but we figured out how to deal with them. Yeah?
There's a class of loop optimizations that are optimizations because of cache locality. I'm thinking of tiling. Have you thought about it? Any thoughts on expressing that sort of thing as a cost function?
So that cache locality and actually parallelism sort of come up a lot when I talk about this stuff. And basically, they have two common issues. The two things have the same issue behind them, which is generally interprocedural stuff. Basically, for cache locality, you typically have to know how memory is laid out, and that's typically not written. That's not available in the function you're working on. So it's hard to make a cost model that doesn't even know how the memory is laid out and stuff. At least that's been when we've done some investigations of this. this is the problem that we always ran into, is that you didn't know like how the memory would be laid out, at least not automatically. So again, if another tool came along and said, here's some information, then we might be able to try incorporating that. But that's one where we didn't have any luck, because we didn't have such a tool.
Okay, let's thank the speaker.